The universe is full of lots of crazy phenomena, but one of the most bizarre is the black hole, an object that generates such intense gravitational fields that not even light can escape. They're real, but there are tons of myths out there about them. I'm going to make a couple of videos about them. Let's start with the basics. Black holes. What can we say about them? Well, let's start with a common misconception, which is that black holes are somehow ravenous monsters that suck everything into them. I mean, you've probably all watched some movie or another where a character says, "Captain, we're caught in the black hole's gravity. We're doomed." And I'm sorry to say, this is more movie drama than science. Black holes don't reach out and grab unwary spaceships. On the other hand, black holes can have very strong gravity, so there's some truth to the claim. So let's dig a bit deeper. Let's start with a fact that might surprise you. For someone far from a black hole, black holes are not all that special. To see that, let's look at some numbers. For example, just how much velocity an object needs to get ejected from our solar system at a handful of locations. This is called the escape velocity, and we'll start with the location of a few planets. Now, I'm not talking about what's needed to lift a rocket off the planet themselves, but rather a rock that is orbiting the sun at the same distance as the various planets. To simplify things, let's just pretend the planets don't exist. So, if we wanted to shoot a projectile located at the Earth's distance from the sun into interstellar space, it would need to have a velocity of about 26 miles per second. If we started with the same projectile at the orbit of Venus, we'd need a velocity of about 31 miles per second. And at the orbit of Mercury, we'd need a velocity of about 42 miles per second. Let's go one step further and calculate the velocity we'd need to have to launch a projectile from the surface of the sun. To get to interstellar space, that rocket would need to have an initial velocity of about 386 miles per second. So those numbers are all for our sun and our solar system. They've got nothing to do with black holes. What happens if we somehow magically erase the sun and replace it with a black hole of exactly the same mass as the sun? If black holes are the scary thing we see in movies, well, then surely the escape velocity for a black hole must be much higher, right? However, when we calculate the escape velocity for that black hole and at the same locations, we see that they are identical. Identical. So this shows at common astronomical distances, black holes are really pretty ordinary. This graph shows more or less the same thing. Distances farther from the surface of the sun have smaller escape velocities. But now let's look at distances smaller than the sun. If we assume that the sun is a uniform sphere, it isn't, but we can assume it is to make the key point, what we see is that the velocity needed to shoot a projectile from a location inside the sun out into interstellar space rises more slowly than it does outside the sun. And as you get closer to the center of the sun, the escape velocity approaches 473 miles per second. And yes, I've ignored the fact that the sun is super hot and friction effects and so on. Details. On the other hand, the black hole I described has all of the mass of the sun, but in a much smaller volume. And as we get to smaller and smaller distances from the black hole, the velocity needed to escape it gets bigger and bigger and bigger. It goes from the 386 miles per second needed at distances equal to the surface of the sun to 1,000 miles per second, 10,000 miles per second, 100,000 miles per second, and so on, until we get to a distance of just shy of 2 miles from the center of the black hole, and at that distance, the escape speed hits 186,000 miles per second. And 186,000 miles per second is the speed of light. Since nothing can travel faster than the speed of light, once you get closer than that, it's impossible to escape the gravitational grip of the black hole. And that's the definition of a black hole, something that exerts enough gravity that light can't escape from it, but, as we've seen, only for super close distances. So that's the first truth. At astronomical distances, the gravity of the black hole is indistinguishable from a star of the same mass, and of course it doesn't emit light. However, at short distances, the gravity surrounding the black hole gets stronger and stronger until it's so strong that light can't escape. The distance from the center of a black hole at which light can escape is called the Schwarzschild radius, after German physicist Karl Schwarzschild, who worked it all out. For a black hole with the mass of our Sun, the distance is about 1.8 miles. For a hypothetical black hole with a mass of the Earth, it's about 1/3 of an inch, or 9 millimeters. By the way, those numbers are for a non-rotating black hole. Rotation complicates things, but we're taking it easy in this video. Just keep that caveat in mind. The sphere surrounding the black hole with a radius of the Schwarzschild radius is called the event horizon. Outside, it's at least possible to escape a black hole. Inside, it's impossible. So that gets us into a super fuzzy area. Many people ask, well, what's it like inside a black hole? And, depending on the scientist, you'll get different answers to that question. Most will tell you that inside the black hole it's empty, except at the very center, where all of the mass of the black hole is concentrated in a point with zero volume. This is called the singularity. However, the honest answer of what it's like inside an event horizon is we don't know for sure. After all, we've never taken any measurement or made any observation from that region of space, so anything we say is simply theoretical conjecture. On the other hand, we do have Einstein's theory of general relativity, which is the leading theory of the behavior of gravity when gravity is strong. That theory has been validated under many conditions, so we have at least reason to believe that it's at least partially accurate within a black hole. So what does Einstein's theory say? Well, it says for one thing that the singularity idea is right. Gravity inside the black hole is so strong that all of the matter is concentrated into a single point. It also says some very weird things about how space and time switch places, but that's the topic of a different video. But let's think about that singularity thing. If you take it seriously and believe you can put the mass of an entire star in a spot of zero volume, that means you have an object with infinite density, and that just doesn't make any sense. When a mathematical theory describing physical reality predicts an absurdity, you need to take another look at the math. And when you do this, you quickly come to the conclusion that the singularity idea is probably wrong. What's probably true is that at very small sizes we need a new theory of gravity, a theory of quantum gravity. I already made a video that talks a bit about quantum gravity, and I put a link to it in the description if you want to learn more. So that's probably a good place to stop for an introductory video. Black holes are ordinary and exceptional. At typical astronomical distances, they aren't really different from any other star, except they don't give off light. As you get closer and closer to the black hole, gravity gets stronger and stronger until it gets so strong that not even light can escape it. That's called the event horizon. Inside the event horizon, we actually don't know what's going on. General relativity, which is the best theory we have of strong gravity, says that the mass of the black hole is concentrated at the center in a space of zero size. That's probably an oversimplified approximation, but we may never know the actual truth since it's impossible to look inside a black hole. In this video, I concentrated on the aspects of black holes that are pretty ordinary. They're essentially heavy stars with the twist that you can't see what's going on inside them. In the next video, I'll tell you not about the ordinary facts of black holes and instead focus on the extraordinary. That video is going to be mind-blowing. See you soon. Okay, you know the drill. If you enjoyed the video, be sure to like and subscribe and share on social media. And also be sure to watch the follow-on video where I talk about some of the crazy features of black holes, places where the laws of physics are bent, twisted entirely beyond recognition, which, when you think about it, sounds very hard to do. After all, physics is everything.